I'm delighted to welcome Professor Ian Ford from University College London, who's going to talk to us about Maxwell's demon and the second law of thermodynamics. Breaker or faker?
Thank you, Harriet, and thank you so much for the invitation to come and speak to you. I'm delighted to be here to participate in this interesting meeting. So I'm here to talk about the second law of thermodynamics, my favorite law of physics, and my favorite imaginary creature of physics, namely Maxwell's demon. This is not Maxwell's demon, by the way. This is his dog, whose name is Toby, I learnt this week. But this is his statue. This is Maxwell's statue in Edinburgh. Maxwell challenged the second law of thermodynamics. That law is the law that the entropy of the universe, of the world, never decreases. And Maxwell challenged this then recently introduced law of physics with a thought experiment involving this imaginary creature, the demon. We'll see what he does later on in the presentation. It's a paradox because the law seems to be broken, and there's been 150 years of people wondering whether the demon is actually breaking the law or whether he's actually just faking breaking the law. Is he a breaker or is he a faker? And I'm going to give you some different perspectives on this matter. So the paradox is the second law of thermodynamics. Entropy, we've all come across entropy in all sorts of contexts. It's a scientific context, it's a scientific quantity, but it's been introduced in all sorts of things. In politics, for example, you read newspapers, they talk about the entropy of the world. And what they mean is the chaos in the world, which is one interpretation of entropy. It is increasing all the time, whatever we do. And Maxwell's demon is supposed to destroy it. So is he a breaker or is he a faker? What is entropy? I mentioned just now that it's chaos. It's the product, the outcome of chaos in the dynamics of the world. And that's actually a correct statement. It brings into play this concept of the arrow of time, that the world is developing from something which happened in the past, which was less chaotic than what is happening in the future. The arrow of time is, again, something that has come into common parlance outside science. What is also said, and I'm distressed to find that in A-level syllabuses in chemistry, entropy is described as the decline of the world, the decay of stuff, things going wrong. I'm distressed to read about this because it's not actually really the modern interpretation. What is the modern interpretation is that entropy is uncertainty, personal, subjective uncertainty as to the state of the world. Bits we cannot see are uncertain to us, and a measure of that uncertainty is this thing, entropy. It's missing information. It's not decay, decline, stuff going wrong. It is missing information. It is subjective. It depends upon what level of measurements we make. This is what entropy is in the modern parlance. So these A-level chemistry students who come to universities expecting to be told entropy is decay, decline, disaster, that's going to have to be a job of re-education, sadly. Chaotic dynamics underpins this growth of subjective uncertainty in the world. I've got to plug a book that I wrote, sorry about this, because I've been interested in entropy for many years, ever since my chemistry teacher at school, Mr. Axel, introduced me to this topic so long ago, I can't quite remember. So let us take a picture of the universe and try to express the chaotic behavior of the universe. Here is a space representing all the coordinates of the 10 to the 86 particles in the visible universe, I guess. And this little particle, this little point, I should say, represents the set of all those numbers. And as time passes, it moves in the space. All those positions, velocities in a classical picture, they all move, they spend different portions of the history in different places. That's what the universe is doing, but we cannot perceive all 10 to the 86 coordinates. What we perceive are bulk quantities, macroscopic, coarse-grained properties of the world. And the way to describe that is to kind of break up this space into sectors that we can perceive. We cannot perceive anything below the size of these sectors. This is the subjective uncertainty that I spoke of just now. This is our limitation, our personal limitations. And I've rewritten that picture in this fashion because it's going to be built on. So these sectors are now circles that represent perceived configurations of the world. And these are possible microscopic configurations of the world. We just don't know which one our world currently takes. By the way, the labeling is letters of the alphabet. There's also colors. We don't worry about the colors at the moment. Just these are different possible states of the world. We don't know which one we're in because we are imperceptive creatures. So this is the present day. One of these is the present day. We don't know which it is. We know that the past was also a configuration, and we know the future was a configuration, will be a configuration too. But we don't know which was in the past. We don't know what will be in the future. We could be any of these in the past, any of these in the present, and any of those in the future. But they are connected. The letters, this H with a star on it, in the past, developed over time, where is it, to this configuration in the present, and in the future will develop into that configuration in the future. There is a deterministic, in the classical point of view, trajectory linking past to present to future, but we don't know what it is. We can't perceive it. We can perceive only things on the macro scale. So this is one possible history of the world, but we don't know if it's ours. However, entropy comes into the picture when we try to imagine possible histories of the world, subject to observations, for example. For example, if we were to observe that the past had a character that confined its configuration to one of these patches, one of these sectors, this one here, for example, then in the future, from the past into the present, those configurations will take their chaotic trajectories, whatever they are, and end up in a different sector, typically. They would spread out because of the chaotic dynamics. And into the future, they would do the same again. There would be a spreading out of the configurations, given that they started out in a small sector. And from this picture, we get our current understanding of what entropy growth is. This is the way that we understand entropy growth, and it's because of Ludwig Boltzmann, hero of science, hero of physics, who put forward the idea that this business of the sector that is currently occupied by our configuration of the world is a measure of entropy. It's that growth that is being expressed in the second law. So he said, what is the likely size of the currently visited sector? And if in the past it was this small size, and in the present it's a little bit larger, likely to be larger, and in the future larger still, then this is mapping onto the idea that there's something growing in time, and that is what entropy is. That's what entropy is. And in words, this is what I've just said. Entropy is the likely size of the perceptible configurational sector that contains the imperceptible microscopic configuration of the world. That's what Boltzmann said. Hero of science. Here's his gravestone. I visited it. Somebody had put a rose on the back of the statue. And at the top there, you can see the second law written in his mathematical form. Hero of science. This is another hero of science. This is Gibbs, who came up with another related and absolutely compatible view of what entropy was, and he simply put it in terms of an information science language. So entropy is the informational uncertainty, that word again, of a subjective probability distribution over the microstates of the possible world, the possible microstates of the world. So that's what entropy is. It increases with time because of chaotic motion. It depends on how we perceive matters. If we look more closely, we don't see as much entropy. This is the second law of thermodynamics. This is what those chemistry A-level students will have to learn if they come and do a course of statistical mechanics. So, okay, I've taken you up to the point of view where we understand what the second law of thermodynamics is. Makes me happy. Now we come to a paradox. This is a paradox called Loschmidt's paradox, which challenges that very statement. There is no arrow of time. There is no arrow of time because the equations of motion of the world are so-called time reversal symmetric. What that means is that there is no difference in the equations of motion that we use for retrodicting the past compared with those that predict the future. There is time reversal symmetry. So there's no reason to say that those trajectories that Boltzmann imagined are any more likely than those which are doing precisely the opposite and going from a large sector down into a tiny sector from the past into the future. Where are those trajectories? That's the paradox. It's another paradox. It's not quite the Maxwell-Demon trajectory. Pictorially, this is our world, according to Boltzmann. It starts out in a small sector, it ends up in a large sector. That's fine, but here is a Loschmidt world where we start out in a big sector, we end up in a small sector. And in this world, the entropy is falling with time. So this is a paradox because we never see these events. So Loschmidt threw a spanner in the works. But this picture can also be used to tell us why, given our world, a world that started small and ended up, or came to the present in a medium-sized sector, why is this world unlikely to end up in a small sector in the future? Well, it's because it's already unlikely to have moved from a small sector to a large sector. That's an unlikely event. It's more likely to have started out in a large sector and ended up in another large sector. The reason that we don't see low, high, low entropy history is that it's so very, very rare. It's possible, but it's very, very rare. So Loschmidt and his Loschmidt trajectories kind of illustrate that. Okay, all right. Now let us talk about the demon. The demon would like to do what we've just said is very, very rare. We have a world where entropy is increasing, and we want to make it turn into a world where entropy decreases. It's very, very rare, but the demon appears to know how to do it to order. You just give him some instructions, and he will reduce the entropy of the world. So how does he do that? Well, Maxwell challenged the second law by introducing this idea of a demon. He didn't call it a demon, somebody else did, but a small and nimble-fingered individual who could manipulate atoms. And what he has is this box and a trapdoor between two cavities. And there's atoms in one side and atoms in the other side. And he is going to sort those atoms into fast and slow. And that will correspond to making heat separate into something that's hotter and something that's colder. And that's breaking the second law of thermodynamics, it turns out. Let's see how he does this. He has a trapdoor, and he has a pair of eyes, and he can see particles as they approach the trapdoor. Now, red means fast, blue means slow, and his instructions are, if you see a red atom, a fast atom, coming from the right, you open the trapdoor. If you see a blue atom, a slow atom, coming from the left, again, you open the trapdoor. That's what he's doing here. Red from the right, blue from the left. In this way, all the reds are going to end up in here, and all the blues on the other side. In addition to that, he blocks the passage in reverse. He blocks the passage of blues wanting to go to the left and reds wanting to go to the right. He blocks those, he lets the others through. That's his job. This is what Maxwell imagined his demon could do. And after a little while, all the reds will turn up on the left and all the blues on the right. And this is a reduction of entropy because it's creating a temperature difference But it's better than that. It's reducing our uncertainty into the configuration of the world. Previously, we didn't know where the blues were. They were anywhere. Now they're all over on the right. We have reduced our uncertainty. That's what entropy reduction is. How does he do this? This is the question. This is the paradox. How does the demon manage to do this? Is he breaking the law, or is he faking breaking the law? I can give you 4 possible resolutions of this. I'm only going to touch upon them because time is short. But I'll give you some ideas as to how this paradox has been addressed and possibly solved in the last 150 years. Now, there's different colours. The 2 on the top in green are where he's actually breaking the law. He's breaking the second law. He's found a way of doing that. He's truly a lawbreaker. So the entropy police, here they come, are really going to collar the demon and deal with him properly. But on the bottom, he's a fraudster, where he's doing his job, but there are unexpected consequences of that job, which actually cloud the issue, and turns out he's not breaking the law at all. He's faking that. Let's talk about item 3 to begin with, where it turns out he's faking. This is actually the most popular so-called exorcism of the demon, which was invented over 40 years ago by Charles Bennett. And here it is. It's based on the idea that when the demon performs the measurement, I said he has a pair of eyes, he can look at the particles and work out if they're red or blue. That is taking a measurement, and that's not for free. You don't take a measurement for free, it turns out. At least this is the resolution. What you do is you perform a measurement, and you remember that you've performed a measurement. This is all a bit vague, but it can be made more substantial mathematically if you develop models of this business of measurement. But this is the idea, that a measurement is made and is remembered. And here's a demon, and he's performed a measurement, and he can remember doing so. So let's have a look at the mind of Maxwell's demon. Back to this picture again. He's measuring the speed of atoms and whether they're heading to his trapdoor, and he wants to let through the red ones, not the blue ones. But he is in an uncertain world. There's nothing so clear to the world around him as that picture suggests. Everything is shrouded, potentially, in uncertainty because he cannot perceive details so easily as we cannot. So he doesn't know what's going on around him. But he can make a measurement. He has the ability to uncloud his surroundings and measure the speed of an approaching atom. And once he's done that, he can open the trapdoor if it's appropriate. Through the trapdoor goes the particle, and he closes the trapdoor again. And then the clouds descend because the world is chaotic and uncertainty grows. So that's his job. That's what he's actually doing. And we have focused on the business of making a measurement there. The memory of making the measurement resides somewhere in the mind of the demon. This is the Bennett exorcism, 1982. And this is not the same demon as before. There's been a storage of something which has to be removed in order to get back to where we started again. We have to reset that demon and remove the memory, the storage of that measurement having been made. That's what's happening here. And this is where potentially the flaw in the scheme arises. What is the cost of removing that stored information? This is what's happening here. The store of information in the mind of the demon is a bunch of arrows, figuratively, and they have to be eradicated, they have to be erased. And this is the process also known as Landauer erasure of information. And it's entropy producing. Models can suggest this is so. So what is the scheme here? What is the exorcism? It seems that by taking measurements and storing information, we are reducing entropy of the world, but we're only doing it for a period of time. There is a loan we take of negative entropy, reducing the entropy of the world, but at the cost of storing information. And eventually we have to pay back that loan. We have to erase that information, pay our entropy cost of doing so, and that puts everything right. That's the exorcism. And we can do it whenever we like, which is a bit of a flaw in the argument, because what if we never do it? What if we never? So it's not so much a law if we can decide whether we want it to hold or not. But that's the issue. Okay, well, here's an alternative which can avoid that flaw, which is that actually what's happening is not that the demon is taking a measurement record, he's absorbing uncertainty from the measured item. The measured item has been revealed, but the uncertainty associated has somehow and figuratively been absorbed by the measuring body. So there's a big fluffy cloud of uncertainty taken on by the demon, by the process of measurement. And that is now to be reset. And that is replacing the scheme previously shown. Figuratively, we have a demon whose internal structures have all been made uncertain to an observer who is measuring the entropy of the world. The structure called the demon is now a much more uncertain object and is a possessor of much more entropy than was the case before the whole thing began. And that has to be removed. And it is not a generation of entropy, it is a shifting of entropy from one place to another that's going on. And this doesn't involve making a loan or trying to work out when to repay the loan. There's no negative entropy being created at any point. So that's what the point of view of putting the mind of the demon into the argument is all about. That's point 3. That's the most popular way of explaining this paradox. Okay, so that is a fake breakage of the second law, because there wasn't any breakage. The entropy was never destroyed in that scheme from this point of view. So let's now talk about another scheme. I think time is fine, so let me continue and talk to you about entropy being produced not in the storage and then the transfer out of entropy into the demon, but rather the mechanics of taking a measurement and whether that is an entropy generating process. Shining that torch onto the particle, did that create entropy? It wasn't a business of transferring it around or stuff. Is the acquisition of information entropically productive? So let me talk now about the so-called Szilard one-particle heat engine. A heat engine is a means by which to create heat, to create work out of heat. You've got some hot stuff, cold stuff, you flow heat between them, you drive a turbine. That's a heat engine. So Szilard, back in the 1930s, challenged the demon by imagining he could operate a one-particle heat engine of this kind. Here it is, except we don't know exactly where the particle is in a box. The demon doesn't know, but he has the capacity to work out something. First of all, he puts a partition in between the top and bottom of the cavity. Then he measures which cavity the particle occupies. He has this ability. Again, it's a vague idea at the moment, but you have to put flesh on that. He measures the position of the particle to some coarse degree to some coarse level of description. It's in the bottom. Now, if there's a particle in the bottom but not in the top, he can use that situation to raise a weight. He puts a weight on the partition. He attaches the whole thing to the world, to a heat bath, and the particle that's underneath the weight bounces up and down, and eventually, if you wait long enough, the weight will be raised to the top of the cavity. In this situation, we're doing work from heat. It's a heat engine. And at the end of all of that, you're back to where you started. The partition's reached the top, the weight has been raised, heat has been absorbed, and you can do it again and again. And this is the part to focus on. This is where entropy is being reduced, because heat is being fundamentally taken from the world and made to raise a weight. And that doesn't happen. We don't see that. That's entropically not allowed. So how do you get around this? How do you explain the apparent lowering of entropy? Okay, well, this whole point addressed whether measurement is entropically costly. And you have to just take a closer look at this business of the revelation of whether the particle's in the top or the bottom of this cavity. It doesn't come for free, and it has to be modeled with mechanics. It has to be taken as a mechanical, as a physical process, not just a revelation. It turns out that when you do build such models, sure, the demon has identified which cavity the particle occupies, but in doing so, he's had to allow a weight to fall. This is the cost of performing measurement. A weight has had to fall, potential energy has been converted into heat, which then goes into the world, into the environment, carrying with it uncertainty as it happens, and that creation of uncertainty is entropy production. So in this diagram, I'm illustrating what is this entropic cost of performing a measurement. When you actually take this scenario seriously and try to model it, you find that there is entropy being produced. A weight has to fall to make this happen. And that's entropy productive. So that's the resolution of this business of another fake demon. He thinks he's performed this heat engine process, but he doesn't realize that he has created entropy in performing a measurement. I'm not sure I have time to go into this, but several years ago, I produced a simple model of this business of measurement and of exploitation of gathered information using springs, as one does. Here's a system, it's a spring. Here's a demon, another spring, and they're connected in some way, and by just solving the equations of motion, correlating these two, and then using the extracted information held in the demon to manipulate the system in such a way as to try to extract work. You can study all of this using models of modern models of thermodynamics, known as collectively as stochastic thermodynamics. And in the end, you follow all the rules, but you find that there is a cost of entropy production in performing that measurement prior to any manipulation of the system using the information you gain. There's a cost. And in the end, the demon fails. He doesn't know that he's had to spend entropy in order to make the measurement. I won't go through that picture. To summarize, another fake demon is one who measures and pretends there is no entropy production in doing so. Okay, I'm going to use my very limited remaining time to talk about the actual potential law breaking that could take place. Let's talk about part one here. The demon can break the law if he has access magically somehow to a different kind of mechanics, a different dynamics, one that doesn't satisfy time reversal symmetry. This is, if you remember, the property of the world where retrodiction and prediction satisfy the same equations, are performed with the same equations. If you have a different world, different dynamics, then you can break the law, it turns out. I didn't want to dwell on these two slides, but if you can focus on one thing, there is a dashed line in red, which is entropy production, which becomes negative if you manipulate those springs in that model in a particular way. If you think of it as just a clever demon performing exploitation of information in a clever way, you can destroy entropy using stochastic thermodynamics, modern day thermodynamics. You can do it. But to do this, you have to introduce time asymmetric dynamics. And that's the way to break the law, the second law. you have to use a dynamics which doesn't seem to satisfy this basic symmetry that we think applies in the world. But that's not news, actually, because when you think of the demon of 1867, that's precisely what he was doing. He was using time asymmetric dynamics to break the law. I'll show you what I mean by that. Here's that demon with his trapdoor. He's looking at the speed of the approaching atom, opening or shutting the trapdoor. This is the rules that he followed. He opens the trapdoor when he sees an appropriate particle coming along. That's time. That is a set of rules. If you look at the time-reversed set of rules, they are the following. If the demon sees a fast atom receding to the left, not approaching from the right, but receding to the left, or a slow atom receding to the right, not approaching from the left, but receding to the right, then he should open the trapdoor. Except there is a problem in doing this. He can't open the trapdoor to let it through after the atom has passed. This kind of set of rules up here is not time reversal symmetric, because this is its time reversal symmetric counterpart, and this is not possible. The dynamics are time asymmetric. And that's how the demon did his job, actually, in 1867. He broke the law. He did break the law. He introduced dynamics which were not lawful. So the entropy police definitely need to investigate. So that's that. This is my last point, and I have gone over time. So I'll just simply say that the final way to break the law is really what Low-Schmidt suggested, which is that you just find a way of accessing one of those entropy-destroying trajectories, which is really hard. But one way of doing so is to reverse the velocities of all the particles in the universe, which is really hard. But if you did so, and that's what they did in the film Tenet, actually, they imagined a world where you could reverse time, but actually reverse evolution in time. That's the way to destroy entropy. But again, it's breaking the law because we don't know how to do this. So I am on my last slide. And I wanted just to summarize a few things. So Maxwell said, yes, build a demon. Here's one. It's just measurement exploitation. But then there are illustrations of some flaws in that argument, starting with this business of the need to forget having made measurements which cost entropy. This is a fake breakage. Then there was a picture of measurement being costly in entropy. Again, this is a fake breakage. There are unexpected sources of entropy production happening in those two cases. If you wanted to introduce new physics, new dynamics, you can break the law. But we don't have access to such things. That is truly a thought experiment only. It is law breaking. The original demon was truly a law breaker. And the final way of breaking the law is to reverse all the velocities, access Low-Schmidt's trajectory. There isn't really a paradox here. There are resolutions of a puzzle, and that's been going on for 150 years. Probably will continue. That's it. Thank you very much for your attention.
Thank you very much, Ian. I was interested to see your heroes of science and some art and some films. So plenty for us to think about, and whether or not we think the demon is a faker or a breaker. I have, lots of questions. I had three in the middle. I'll take the lady in the middle of this row here, and then the gentleman further along to her left after that. And then I'll take you at the back.
Hi, I followed most of what you were saying. I was interested that when you were looking at your model analogy, that you weren't looking at the energy he used to open the door, or does that take you into the Gibbs energy thing? And are we just looking at the entropy? Because obviously he's then having to expend quite a lot of energy opening and shutting that door, and that wasn't investigated. And have I missed something?
You're absolutely right. It would seem necessary to include the opening and shutting of the door and friction that takes place there, which is entropy productive. Yeah, in the original argument, it was imagine a frictionless door. So that's the way out of that one. In reality, yes, you would have to. Yeah. You throw away things that, you think are not so crucial and focus on other things.
So I've got this gentleman.
Hey, great. Thank you very much for a really good talk. I'm afraid I probably did the wrong subject. My physics teacher at A-level didn't even mention entropy. So there we are. A quick question. This is all classical. Does anything change if you look at the quantum world? Or is there an equivalent Maxwell's demon?
That is a very good question, a very deep question. I don't know really. I would like to think it's just the same, actually. I would like to think that instead of 10 to the 86 coordinates in the universe, there are gazillions of quantum amplitudes, all dynamically evolving in just the same way. We don't know which one it is, which quantum state it is, so we sectorize, and then we talk about the entropy of which sector we're actually occupying. I'd like to think that's exactly how it is. There is a problem, though, in quantum mechanics of measurement being particularly different, but even that could also look rather similar to classical measurement, namely that there is a mechanics to it and a dissipation of energy into heat in it, which is entropy producing. So I'd like to think it's just the same.
Thanks for the fascinating topic and talk. Just a question, is the second law not just a probabilistic effect? Because if you consider the two chambers with the demon and you have only one particle, you've got a 50-50 chance being right or left. If you have a second particle that's independent, completely independent of the first, you've got a 50-50 chance being right or left. So to have both in the right side, you've got a 25% chance. If you add another particle, you still got a 50-50 chance, so then you've got an eighth of them being all together. So statistically, eventually, there's a slight chance, but there is a statistical probability they'll be all in the right chamber. Now, the chance is very small, but it doesn't involve, you don't have to go against the law of entropy or energy or anything. It's just a statistical probability that you will end up with lower entropy than, even without a demon.
You're absolutely right, which is what Maxwell said in 1867. He said that a small number, or indeed a finite number of particles, potentially could, just by chance, all accumulate in the corner of the room, just by way of bouncing.
Isn't that what Loschmidt said then?
Loschmidt was talking about reversing trajectories, and so I guess that would be a reversed version of the expansion of particles out of the corner into the room. It is feasible to break the second law, to introduce more certainty in the configuration, to reduce the sector absolutely naturally and spontaneously. That's what Maxwell was saying. He was challenging the second law. That is also the current view of the second law in this framework of stochastic thermodynamics, which allows fluctuations in the entropy production, allows negative changes. It's absolutely part of the model that entropy can fluctuate down as well as up. The second law these days is that there is a tendency on average for entropy to rise, but not that it should never fall. Fluctuations are no part of the deal.
Okay, so I have the gentleman in the white shirt there, the gentleman down here in the blue jumper, and then I had Jim over here.
Okay, thank you. Thanks, Ian. Great talk.
Hi, John.
As you probably know, in particle physics, there is a time asymmetry, a very low level of time asymmetry. Has anyone thought about building an actual daemon that exploits that?
Aha, okay. Well, that's of course, I guess that is the way to do it. If you can find a particle process that weakly breaks time reversal symmetry and employ it in exploiting knowledge, show me, tell me. The time reversal symmetry is not unbreakable, so maybe the daemon just has to find that legal way of proceeding.
A very insightful presentation to Maxwell's daemon. Is it that you were really arguing against preconceptions in the interpretation? Because they're all really preconceived ideas. You were uncovering them. Is that right?
Yes, yes. Other people have uncovered them. Bennett uncovered them. And Brillouin, actually, prior to Bennett, I didn't mention his name, but he was a proponent of the cost of measurement, the entropic cost of measurement. So yeah, people have uncovered and challenged these preconceived notions of measurement, how it's cost-free and just free to do.
Can I ask second part of my question? Yeah. Another possibly anomaly against the second law of thermodynamics is a mixed granular media. When you shake stuff, possibly the grains with large size come to the surface. And apparently it defies the second law of thermodynamics. Can you bring clarity to that?
It's not a closed system. Entropy in a closed system will rise. This is not a closed system. If you've got a box full of granules, you're shaking it around, there's all sorts of exchanges of momentum with the external world, and so it's not going to satisfy.
Thank you.
Thank you. Hi, Ian. I liked your point about the demon not having to retain the memory because, you know, obviously erasing his memory and that has an entropic cost. He doesn't have to. He can keep, as long as his brain is big enough to hold the information, he never has to forget about it. But he memorizes all the particles at the positions in the box without actually opening and closing the shutter. He's presumably increased algorithmic entropy in his brain. You know, if he starts off as a blank slate, his brain has increased in complexity, increased information. But then he does the measurement, and that has an entropic cost. There seem to be, he's lowered the entropy of the box, but there seem to be two increases in entropy, one in the measurement process and the other in increasing the complexity of the entropy of his brain.
Certainly there's, if he takes all his measurements before exploiting any of them, he never gets the benefit of the measurement. He never gets the benefit of having acquired the information. But he still pays the cost of the measurement. So the entropy is produced in the measurement, and the entropy is produced in storing the information.
Yes.
They're a combination of two things. He's paying doubly before he ever gets to exploit it. Then he's happily going to sort everything with little entropic cost, actually. That ought to be perfectly free. He opens and shuts the trap.
That's fine, yes.
And just does the job. But he's paid up front.
Well, he's paid in making the measurements, that has an entropic cost. And then at some later point, arbitrarily in the future, he could also increase external entropy again by erasing his memory and heat waste.
Yeah, there's a lot of entropy being produced in both of those periods.
So I'm going to do a suite of three now. So I've got a lady here, I've got the lady in the green jumper here, and then the gentleman just in front of her.
Okay, thank you for the great presentation. I've got two quick questions. The first one, can you further clarify the definition of the closed system? Because intuitively, for me, the demon experiment seems more like the demon acts like an external factor that injects further information into the system so that it can reduce the entropy. It's not a really closed.
You're absolutely right. This idea that the demon can extract information while not actually creating an open system is incorrect. Extraction of information opens a system. It's no longer closed if the demon is interrogating it. So that's absolutely right.
Okay, great, thank you. And my second question is for the Loschmidt trajectory, because entropy arises from misinformation, so it can only apply to probabilistic scenarios. It can't really do anything with its deterministic process. But if we have a Loschmidt trajectory, if we can know the velocity, position, know every information in that system, it seems like a deterministic situation now instead of a probabilistic one. So is that really a law breaker, or just entropy definition is no longer applicable in this scenario?
The dynamics is deterministic. It's in these illustrations, there is no randomness in the dynamics. What is random is the initial condition, or what is uncertain is the initial condition. The Low-Schmidt trajectory just requires a particular initial condition, a very, very special one that leads deterministically to the destruction of entropy. So it's just finding that configuration. That's the tricky part. And in this world of ours that has a low entropy past, finding those trajectories naturally is exceptionally difficult. It's just not practical to find those possible but highly rare trajectories.
So briefly, these two last questions.
Claude Shannon defined information entropy as the negative reciprocal value of probability. So are we saying that probability is subjective, causal, and objective simultaneously?
Is subjective, causal, and objective simultaneously?
Yeah, because at the top you said entropy is uncertainty, not chaos. It is missing information. It is subjective. It depends on your knowledge.
Yes.
So are we saying that probability is subjective, or is it an objective mathematical
I would say
object?
so, yes. I would say probability is an expression of our ignorance, of our uncertainty. It is simply that. So it ties in with Shannon entropy being a measure of uncertainty.
You use the perception of an observer to define entropy. Is there any connection, maybe even just philosophical, between an observer in thermodynamics and an observer in quantum mechanics?
Okay, that's okay. I'd say there is an equivalence because an observer in classical physics disturbs the system, just as an observer in quantum mechanics disturbs the system. They have a more radical disturbance in quantum mechanics by collapsing the wave function or sending the wave function to an eigenstate. Whereas in classical physics, they don't disturb the system so much, but they do disturb the system. So an observer is not a free, they're not a non-participant in the process. They do participate in the process, whether classically or quantum mechanically. So this business of entropy arising from the measurement arises from that participation. The measuring device, the daemon, is participating in the process, and that's where the entropy arises. It communicates effect, it pulls uncertainty out of the system to reveal its state. So there is a similarity, absolutely.
Okay, please join me in thanking Ian for his talk.